now turn our attention to the design and selection of springs. Our goal when we are designing springs is to provide a reliable, predictable, repeatable force over prescribed deformation for a chosen design lifetime. The basic types of springs that we will discuss include helical compression springs, helical extension springs, conical springs, torsion springs, leaf springs, and disc or Bellevue springs. Of course, we also have to consider the possibility of air springs, and we also want to talk about something called strap springs. Where do we use them? All you have to do is look around your house. I took my iPad and went outside, looked at my truck, and found a coil spring supporting the front suspension of my truck and leaf springs supporting the back suspension. I also found a nice little coil spring supporting the back suspension of my electric scooter. I noticed a measuring tape is a strap spring because it provides a constant recoil force. I also looked at my garage door and noticed that at the top of my garage door there are torsion springs that apply an upward force on the garage door to make it easier to open and close. So if you look around your house, look around your apartment, wherever you live, you will find lots of examples of springs. And in every case, somebody had to take the time to design those springs. Now let's take a minute to look at a CAD example of a spring, and you'll notice that I have a top and a bottom disc that are applying load to this helical compressive spring. You can see the number of coils here. I will hide the top and bottom discs so you can better visualize the spring during its compression. When you look at the spring, you'll notice a number of important things, and that is the spring has a specific number of coil wraps from top to bottom. You will also notice that the top and bottom have a flat ground face so that the load plates, which I put back here, can apply a nice uniform load to the top of the spring. The other thing that you will notice is if you compress this spring, at some point during the deflection, the coils are going to touch each other. And so the spring goes from a nice elastic deformable body to a much more rigid body that offers a much higher spring constant. This is an example after the load has been applied, and you'll see that we have these stress concentration points up here at the end of the ground flat portion of the spring. And so if we were to cyclically load this, you would expect fatigue crack propagation to start at a location somewhere near there. It may or may not be there. We got to do a full stress analysis before we would really know. There's value in animating it so you can see what happens as we load and unload the coil spring. The stress builds up, the coils get closer together, and so we need to figure out what the stresses are in the spring so that we can design it so that it does not yield. We can do the same thing with the tension spring, apply loads and animate the load displacement response. You'll notice the difference with the tension spring is that the coils are starting in contact and you're simply pulling those coils away from contact. And so the stress distribution is going to be different and the location of failure will be different. We need to know the stress state in order to design these things to prevent failure. The last example is a torsion spring, which applies an elastic torsional response about the center axis of the wound coils. So I emphasize again that the springs must be designed. So we have to understand what loads those springs have to support. How much will those springs deflect and how long must they last? This leads us naturally to start thinking about what the force displacement relationship is for a spring. Now let's in this case just imagine a simple classic spring like we see in physics. We fix the spring on the left side and we apply a force F to the right side, and I want to know how that force is related to the deflection that occurs at the end of that spring. You know, of course, that the force deflection relationship will be linear and that the slope of that line is the spring constant K, so that the force F is equal to K times X. There is a linear relationship between load and deflection for linear springs. And so it's pretty straightforward. If we have a design deformation of some maximum amount, we want to make sure we maintain linearity in the force displacement relationship up to some maximum load level for that maximum displacement, and that would help us to select a spring that would meet that situation. In some instances, we might actually require a stiffer spring. And so if we had a stiffer spring and it was subject to the same deformation, the force would actually be higher. We could also choose a softer spring. So we have some choices that we can make in terms of the spring stiffness whenever we are selecting springs or when we are designing springs. Now, when we're doing our design, if we want the spring to behave the same way every time we load it, then we want to stay in the linear elastic regime of loading. And so we want to avoid the possibility of loading beyond the elastic limit. So if we continued to load this spring here, at some point it would yield and the stiffness would change. And so we want to avoid yield. If we are repeatedly loading it, want to avoid fatigue failure. So we get to the same old problems we've encountered many times, and that is we need to understand the stress state inside the spring so that we can design the spring to prevent yield and to prevent fatigue. Let us begin our analysis by confining our attention to the case of helical compression springs. So you can see that the spring is wound in a helix, and it is designed to be able to carry a compressive load, F, and it's going to compress by some amount delta under the influence of the applied loads. Now, we want to prevent this thing from failing, so we want to prevent yield. So we need to look at how this material is loaded. This is a cross-section of that spring. The diameter of the spring wire is D, and that the diameter of the coil itself across the width of the spring is capital D. So we have the diameter of the wire as little d, the diameter of the spring as capital D. If we move the line of action of the force F to the centroid of the wire, we have a force F, and we're also going to have a torque T, which is going to be equal to the applied force times half the overall spring diameter. That is capital D over 2. So if you look at that section of the wire, you can see that we are going to have both direct shear and torsional shear acting on the wire. So let's look a little bit more closely at that section of the spring wire. We have said that it is of diameter D, and we have a direct shear force F, and we have a torsion T. The torsion is going to be the force that we apply times capital D over 2. This is going to give rise to torsional shear, tau, I'll call it torsion, equal to TR over J. And R is the distance as measured from the centroid to a region of interest along the diameter of the wire. Now, you understand that as R gets larger, the torsional shear gets larger, so we only care about the outermost elements along that wire. And so the torsional shear is just going to be equal to the torque FD over 2 times the outermost radius, well, that's little d over 2, and that is divided by J, which is the polar moment of inertia, and that is pi d to the 4th over 32. And so the torsional shear is just going to be by 8F capital D divided by pi lower d. Our direct shear is simply the force F acting over the cross-sectional area of the wire. So that is just F divided by pi d squared over 4. The maximum shear stress, that's all I'm thinking about right now. And so if you come to a little volume element out here, both the torsional and direct shear are acting downward. And so on that face, we have the sum of the torsional and direct shear. On this little face area over here, we would have the difference between the torsional and the direct shear, because the torsional shear would be facing up and the direct shear would be facing down. So the worst case location is on the inner diameter of the wire. And so the maximum shear stress is the sum of the torsional and the direct shear. And so what we're going to end up doing is trying to compare that maximum stress to the shear yield strength. So we want to know the shear yield strength of the material and make sure that our maximum stress is below the shear yield strength. But before we do that, we're going to introduce a constant C called the spring index, capital C, which is just equal to capital D divided by lowercase d. And we are going to rearrange this maximum shear stress equation written in terms of this spring index, which gives me my maximum shear stress being equal to 8F capital D over pi d cubed times the quantity 2c plus 1 over 2c, and this is called the shear stress correction factor. So we can rewrite this maximum shear stress equation as Ks, the shear stress correction factor, times 8 times the applied load, the spring coil diameter capital D, divided by pi lowercase d cubed, that is the wire diameter, with this shear stress correction factor being defined as 2c plus 1 over 2c. So that's one step that we can take to express the maximum shear stress. Now, this first approach that we talked about, where we express the maximum shear stress in terms of the shear stress correction factor, it turns out that's an oversimplification. And so if you do a more careful analysis considering the torsion applied to a curved coil, you find that a better approximation is the Berg-Strasser correction, KB, which is given by 4c plus 2 over 4c minus 3. And so usually the maximum shear stress is written as the Berg-Strasser correction factor times 8 times the load that's applied to the spring times capital D divided by pi lowercase d cubed. And that's what we will do for the rest of these lectures on helical springs loaded in compression.